Look at the sheer scale of a modern city. Millions of lights, moving vehicles, and data streams, all demanding continuous power. Keeping this running requires an immense, constant flow of energy. And right now, almost all of our portable technology relies on a single, invisible engine to do it. That engine is the lithium-ion battery. It's the silent workhorse tucked inside your smartphone, your laptop, and the electric cars navigating those streets. But we are hitting the physical limits of what this specific chemistry can do. Charging it takes time we often don't have. The internal cells degrade after a few hundred cycles, and manufacturing them requires a constant supply of rare, increasingly expensive materials extracted through fragile supply chains. We are trying to power a global energy transition, shifting entire economies away from fossil fuels, using an aging chemical framework that was never meant to scale up to the size of human civilization. So the tech industry has been pitching a savior, a single technological upgrade that guarantees your phone reaches a full charge in 5 minutes, and an electric vehicle can drive 1,000 kilometers without stopping. They call it the solid-state battery. It sounds like the perfect successor. But can one single battery design actually carry the weight of the entire world's energy needs? The short answer is no. Searching for a single, universal replacement for lithium-ion ignores the reality of how materials and economics actually behave at scale. To understand why, we have to look inside. This diagram shows a cross-section of a battery cell. Notice how the liquid center we use today is swapped out for a dense, solid block of material. That is a solid-state architecture. By removing the liquid, everything improves. Watch how the energy moves straight through that solid core. There is almost no resistance, no dangerous heat buildup. It charges faster, holds more power, and dramatically reduces the risk of fires. But building that dense, solid core in a laboratory is vastly different from mass-producing it. These cells are incredibly expensive to make. They require extreme manufacturing precision, and attempting to scale them up has led to consistent real-world testing failures. You get incredible performance, but the massive price tag makes it impossible to put into every device. We cannot build a global infrastructure on a battery that only a fraction of the world can afford. Since we can't instantly jump to a fully solid state, manufacturers have had to pivot. They need a solution that works right now, utilizing the production factories we already have. That compromise is the semi-solid battery. It mixes the traditional liquid approach with some of the new solid materials to create a practical hybrid bridge. And it is already out in the wild. Companies are actively testing these semi-solid cells in commercial drones that require longer flight times, and they are rolling out in early-stage electric vehicles to push driving range higher. Progress usually relies on these imperfect stepping stones. We keep the transition moving forward today, while the heavy engineering gets ironed out for tomorrow. But personal transportation and pocket electronics are only half the equation. Look at a massive wind farm or an industrial power grid. When you start talking about powering entire cities, the rules completely change. A city does not care if a battery charges in 5 minutes. It does not need a luxury, high-performance cell to store solar energy. At a civic scale, the only metric that matters is cost per kilowatt hour. This is where the real heavy lifting happens, the sodium-ion battery. It trades away high-end performance in exchange for basic ingredients that are incredibly cheap and globally abundant. Sodium is everywhere. By using it, manufacturers bypass the need for rare metals entirely. You strip away the bottleneck of global supply shortages and the geopolitical tension of fighting over mining rights. You can build thousands of these cheap cells to capture massive amounts of renewable energy. True energy independence requires storing power for national grids, and that requires an unglamorous, highly affordable workhorse. Fast forward to the year 2035. And the idea of relying on a single battery chemistry is completely gone. This graphic breaks down future infrastructure. Top tier, solid-state batteries power luxury vehicles and robotics. Middle tier, refined lithium-ion remains the standard for everyday devices. The massive foundation, cheap sodium-ion cells store energy to run smart homes and stabilize national grids. By assigning the right chemistry to the right job, the economics finally work. Electric vehicles drop below the cost of petrol cars, and countries can store enough clean energy to securely turn off their fossil fuel plants. The battery revolution of the next decade is about moving past the search for a miracle. We are building a specialized ecosystem driven by choice, and it is already powering up.